Hi, for today's lesson, we'll continue to learn more about non-homogeneous second-order differential equations. A non-homogeneous second-order differential equation is a differential equation that has the second derivative as the highest derivative and the equation is not equal to zero. The solution to this type of differential equation is the sum of the homogeneous versions and particular solutions version. So, for example, it may look like this, where we have a y is equal to yh plus yp, where yh is the homogeneous and yp is the particular. For our first example, we have d squared y over dt squared plus 6dy over dt plus 8y is equal to e to the minus t. Our initial conditions are y of 0 is equal to y prime of 0 is equal to 0. So this can be rewritten in this form. These two tick marks mean second derivative. This is the second power, so second derivative. This is the first derivative, so just one tick mark. So we can rewrite this equation as y double prime. These tick marks are also known as primes. So y double prime plus 6y prime plus 8y is equal to e to the minus t. To solve this, we need to use the definition. So we need to solve for a homogeneous and particular solution, and we add these two together to get our final answer. So our homogeneous version is just the version equal to 0. So y double prime plus 6y prime plus 8y is equal to 0. In order to solve this, we need to use y is equal to e to the rt. R is just some number, some constant. This is just a general form of how you'd solve this type of second order differential equation. So we let y equal to e to the rt, y prime is equal to r e to the rt, and y double prime is equal to r squared e to the rt. These derivatives were found using the chain rule. So now plugging these values in, so we plug r squared e to the rt for y prime. And then we add 6 y prime, which is r e to the rt, plus 8 times e to the rt, which is y. So now we have r squared e to the rt plus 6r e to the rt plus 8 e to the rt is equal to 0. We find that we can pull an e to the rt out, and we get our characteristic equation. R squared plus 6r plus 8 is equal to 0. This form where we have the r, the constants, up in the exponent, this is just called the characteristic equation. So now that we have this, we find that we can get two terms. R plus 4 times r plus 2 is equal to 0. Because if we multiply these together, we'll get r squared plus 6r plus 8. So now this leaves us with two r values. R is equal to negative 4 and r is equal to negative 2. So now we have two solutions because our original form was y is equal to e to the rt. So our first solution, y1, is equal to e to the minus 4t. And our second solution, y2, is equal to e to the minus 2t. The homogeneous version is just the sum of these two. So y homogeneous, is equal to c1 e to the minus 4t plus c2 e to the minus 2t. These constants are here, and they will change based upon initial conditions. Now, we need to go back and find the particular solution yp. So to find yp, we're going to go back to our original second-order differential equation, y double prime plus 6y prime plus 8y is equal to e to the minus t. However, we're going to let y is equal to k e to the minus t. K is just some constant. So when thinking about this differential equation, we want this term to equal e to the minus t. So this term, it might be of some form of e to the minus t, some number maybe, multiplied by e to the minus t. So we need to verify this. So let y equal to k e to the minus t, y prime is equal to negative k e to the minus t, and y double prime is equal to k e to the minus t. So now we plug these values back in for y double prime, y prime, and y. So now we have k e to the minus t plus 6 times negative k e to the minus t plus 8k e to the minus t is equal to e to the minus t. We find that they all have an e to the minus t, so this pulls out. And we have these k terms in here, so k minus 6k, let's say k is equal to 3k. We get the 3k is equal to 1, which implies that k is equal to 1/3. So our particular solution is 1/3 e to the minus t. So our particular solution is a form of this. So now, this forms our general solution. Y of t is equal to c1 e to the minus 4t plus c2 e to the minus 2t plus 1/3 e to the minus t. However, we were given initial conditions, so this is not our final solution, but now that we have this general solution for any other initial conditions given, we just plug in as necessary. So we're going to use our first initial condition, y of 0 is equal to 0. So when evaluating these initial conditions, you often want to start with the original function and then move on to this type right here. So now, we're using yt, we get 0 is equal to c1 e to the 0 plus c2 e to the 0 plus 1/3 e to the 0. We just take the general solution, plug in 0, because t is 0, and the y is 0. Then we get c1 plus c2 is equal to negative 1/3. This 1/3 would come over here, so that's why it's negative. So now our derivative of yt, our general solution, is negative 4 c1 e to the minus 4t minus 2 c2 e to the minus 2t minus 1/3 e to the minus t. So these were derivatives are found using the chain rule. So now we plug in our conditions where t is 0 and y of t is 0. So we have 0 is equal to negative 4 c1 e to the 0 minus 2 c2 e to the 0 minus 1/3 e to the 0. We get two equations. c1 plus c2 is equal to negative 1/3. And we also get this equation here, 4c1 plus 2c2 is equal to negative 1/3. This can be divided by 4. We get c1 plus 1/2 c2 is equal to negative 1/2. We have two unknowns and two equations, so we can solve for c1 and c2. Now this is a matrix method. This is one way of solving for it. There are other ways, but these are the two equations. So using the matrix method, we're just going to put the coefficients in for c1 and c2 in this. So our c1 plus c2 is equal to negative 1/3. This is a 1, this is a 1, this is negative 1/3. So we write 1, 1, and negative 1/3. c1 plus 1/2 c2 is equal to negative 1/2. We have 1, 1/2, and negative 1/12. This is not 1/2, this is negative 1/12. So now we have it in this form rather than carrying the variables everywhere. We just have all these numbers, and now we can begin using row operations. So we're going to multiply negative 1, clear this 0 out, and then now we're left with 1, 1, and negative 1/3 on the top row, and on the bottom row 0, negative 1/2, 1/4. We're going to multiply by 2 because we want a 1 right here. This will make more sense once we solve it. So now we have 1, 1, and negative 1/3, 0, 1, and negative 1/2. We're going to multiply negative 1 and add these rows together. So we have 1 and 0, 0 and 1, 1/6, negative 1/2. So this value right here is c1, this value right here is c2. So this implies that c1 is equal to 1/6 and c2 is equal to negative 1/2. If you're not familiar with this matrix method, there are other ways to solve this, but you will get two values. So c1 is equal to 1/6 and c2 is equal to negative 1/2. So finally, we have our solution y of t is equal to 1/6 e to the minus 4t minus 1/2 e to the minus 2t plus 1/3 e to the minus 2. For our second example, we have another second order differential equation. D squared y over dt squared plus 36y is equal to e to the minus t. However, we have different initial conditions. Y of 0 is equal to 1 and y prime of 0 is equal to negative 1. So we can rewrite in this form, very similar to this differential equation. Y double prime plus 36y is equal to e to the minus t. However, we don't have this term right here in this specific equation. So our homogeneous version is just this equal to 0. So y double prime plus 36y is equal to 0. Like the previous example, we are also going to get a characteristic equation by letting y equal to e to the rt. Y prime is equal to r e to the rt, and y double prime is equal to r squared e to the rt. After simplifying, we get r squared plus 36 equal to 0. Then we get r squared is equal to negative 36. But this implies that we get imaginary numbers. And when we get imaginary numbers, we need to use Euler's formula in differential equations. So basically, when we have imaginaries, what Euler discovered is we can break this into a sum of cosine and sine. So now that we have this, so e to the I theta, well, our real part is 0. We just have an imaginary part right here, 6, so 6i. So we get y1 is equal to e to the 0 plus 6it, and y2 is equal to e to the 0 minus 6it. What's important to notice about these type of differential equations is although we have the cosine plus I sine theta, at the end we will get a combination of cosine and sine. So our y1 is equal to cosine 6t and our y2 is equal to sine of 6t. So our homogeneous answer, YH, is equal to C1 cosine 6t plus C2 sine of 6t. So this imaginary part can be broken down to cosines and sines. Now to find YP, we need to go back to our original differential equation. Y double prime plus 36y is equal to e to the minus t. However, like this example right here, we're going to let y equal to k e to the minus t. K is just some number because we want to get this side equal to this side. So we want it to be this form. Y prime is equal to negative k e to the minus t, and y double prime is equal to k e to the minus t. And then we get, after plugging these values in, so we're going to plug k e to the minus t for y double prime, and k e to the minus t for 36 y, well, right here. We're going to plug it in right here. So k e to the minus t plus 36 k e to the minus t is equal to e minus t. The e minus t cancels, and then we get 37k is equal to 1. This implies that k is equal to 1 over 37. So our particular solution is equal to 1 over 37 e to the minus t. So now that we have this, we can form the general solution y of t is equal to c1 cosine 6t plus c2 sine 6t plus 1 over 37 e to the minus t. However, we need to use these initial conditions. So we want to start with the y0 and then move on to y prime. So now we have, using these conditions, 1 is equal to c1 cosine 0 plus c2 sine 0 plus 1 over 37 e to the 0. We plug 1 in here because that's the y of t. And this right here is the t value. So sine of 0 is 0, and the cosine of 0 is 1. So we get c of 1 is equal to 1 minus 1 over 37, which is equal to 36 over 37. The derivative of our general solution, y prime of t, is equal to negative 6c1 sine 6t plus 6c2 cosine 6t minus 1 over 37 e to the minus t. After plugging in our numbers, we get negative 1 is equal to 0. This term right here goes to 0 because that's a sine. Plus 6c2 cosine 0 minus 1 over 37 equal to the 0. This implies that 6c2 is equal to 1 over 37 minus 1. And then finally we get c2 is equal to negative 6 over 37. So the derivative of cosine is negative sine, and the derivative of sine is cosine. Now that we have our c1 and c2 values, we plug these back in right here and here to get our final solution. Y of t is equal to 36 over 37 cosine 6t minus 6 over 37 sine 6t minus 1 over 37 e to the minus t. So I hope this helped you in understanding how to solve different types of non-homogeneous second-order differential equations, and thank you very much for watching.